So let's do a little bit of this here together, and then I'm going to stop and let you guys kind of work on your own. Does that sound okay? All right. So the first, 4 questions say, given the vectors, yada, 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 find the component form and sketch the following resultant vectors. It says also be sure to sketch the original vectors as well. Okay. So first thing I'm going to do is I'm going to get the component form for the vector u plus 2v. So first thing I'll do is that scalar multiplication there. And when I add those together, then I get the vector 1, 9. Everybody's okay with that idea? So this is the resultant vector. That's our final answer. Now let's draw our picture of kind of what's going on. So the first thing I'm going to do is I'm going to plot vector u. So to do that, I'm going to go 3 units over and 1 unit down. Oops. Yep, that's what I meant. Thank you. So there's my vector u. And now from vector u, I'm going to graph vector 2v. Actually, let's actually do it this way. Let's graph vector v, and then we're going to do it twice. So here I'm going to go 1, 2 units to the right, and then 1, 2, 3, 4 units up. And then I'm going to go 1, 2 units to the right, and then 1, 2, 3, 4 units up. And then my resultant vector is that one. Yep. So 2v, I just did v 2 times. It's fine if you did it 2v as one vector also, but that's what scalar multiplication is really saying. You're just doubling the length of that vector. So it stays in the same direction. The direction stays the same, but the length becomes, 2 times as long. So it's like the same vector twice. So that's kind of what the picture would look like. And again, remember the key here is that when we add vectors, they add head to tail. So the tail starts at where the last one ended. And then our resultant vector goes from the origin to the last head. Does that feel okay there? So let's move on and do one of the other types. Is everybody okay with that plan? Okay. So it says, find the magnitude and direction for the following vectors. Use reference triangles to help find your angles. Leave all angles in degrees and round to the nearest hundredth. Okay, so I'm going to find the magnitude first. So the notation we use for the magnitude of vector p is we use those vertical bars. And the magnitude calculation is just the x component squared plus the y component squared, square rooted. And I'm going to type this into my calculator to get the decimal, since it says round to the nearest hundredth. So I would say 6.32 is my magnitude. Everybody okay there? The direction is going to be a little bit trickier. So to get the direction, I'm going to start by drawing a picture of this vector in the xy plane. So here I'm going to go 2 over and 6 up. And I'm going to draw my reference triangle here. So when I draw my reference triangle, it's always going to the x-axis. It never goes to the y-axis. So because I went 2 over and then 6 up, the side lengths for this triangle are 2 and 6. And what I'm interested in here is this angle here that I'm going to call theta. So since this is a right triangle, I can use SOHCAHTOA. And because I'm given the opposite and adjacent sides, I'm going to use inverse tangent to find this angle measure. Tangent is opposite over adjacent. So to find that direction, I'm going to need to use inverse tangent of 6 over 2. So when I do that, making sure my calculator is in degree mode, I get 71.57 degrees. So that's my direction. Is everybody okay there? Where does the direction get a little bit tricky? Yeah, if you're not finding the direction in the first quadrant, it's a little bit tricky. So let's look at, say, number 7. And we're just going to find the direction here. I'm going to leave the magnitude for you guys. But this one's a little bit trickier because here the vector is not going to be in the first quadrant. So if I graph -3 over and then 2 down, my vector r is like here, right? So if I draw my reference triangle, this was 3 over and 2 down. So the angle that I'm going to find here, I'm going to call alpha. But that's not the direction that I'm looking for. The direction that I want is this one. I'm going to call that theta. So what's the relationship between theta and alpha? Well, you'll notice that the last axis that I passed before getting to the terminal side of my angle was the y-axis. I'm sorry, is the x-axis. We had said when that's the case, we're going to be adding. So theta is going to be 180 plus alpha. All I have to do now is compute what alpha is. Well, alpha is this angle here inside of a right triangle, so I can use SOHCAHTOA. I know about the opposite and adjacent sides, so I can use tan inverse of opposite over adjacent. Which is going to give me 33.69. So when I add this together, I get, what, 213.69 degrees. Is everybody okay with that? Okay. Again, you still need to find the magnitude for that one, but I figured we should do another direction example where you're not in the first quadrant. It's a little bit more to do there, but not so much more, right? Okay. Last one is number 9. It says, given the magnitude and direction, find the component form and linear combination form for the following vectors round to the nearest hundredth. Okay. So the component form is the one with the wedges. And this was basically the question from the homework quiz. So I can just do the magnitude times the cosine of the direction, comma, magnitude times the sine of the direction. So that tells me that, oops, this is the component 507, comma 1088. Everybody's okay there? It asked also for the linear combination form. That's the thing with just the i's and the j's. So the I is just the x component, and the j is just the y component. We remember that the vector I is the vector 1, 0, and the vector j is the vector 0, 1. So if I add those two vectors together, I'm left again with the component form that we have above. So that's your linear combination form. Once you have the component form, it's trivial to get it, right? You just put an I, vector I after the x component, an addition symbol, and the vector j after the y component. That's it. No big deal. What do you guys think? Kendall? Yeah, of course. Uh-huh. Okay. So when we're graphing the negative, so you want to look at 3 then is what you're asking about? Okay. So let's start by doing the computation first, and then we'll graph afterwards. Is that okay? Okay. So when I do that, I get -2, -4, plus -6, +9, which gives me -8, +5. Okay there? Okay. Okay. So how do I want to say this? So here's a situation where I would probably just graph this. So if I were to be really technical, 2/4 up, and then because of the negative sign, I would draw that going in the opposite direction. But that doesn't really help us in terms of drawing the resultant vector, because we need that first vector to start its initial point to be the origin. So it probably makes more sense to just draw -2, -4 there. Yeah, in all reality, it probably makes the most sense to think about it that way. Is that okay there, Kendall? And again, just like on this previous one where I graphed like 2v as v twice, if you drew 2v as one vector, again, that's fine. Not a big deal to me. So if you draw the negative vector as just, like without just flipping the direction, but actually translating it so it's back at the origin, that's fine. And it makes the most sense to kind of do it that way for this one. And I would do the same thing for like a subtraction problem, like one of these. I just think about it as plus the negative vector when I'm drawing my picture anyways. That makes the most sense, I think. Okay with that plan? I'm going to give you guys, say, 20 minutes or so right now to kind of work on this, now that we've kind of gotten a jump start on it. And at 8:30, regardless of where you're at, you're going to pause and we're going to talk a little bit about the next section. Obviously, we're not going to be able to finish the next section in 20 minutes or something, which is all that we have left at that point, but that's my plan. So let's look at the next section. So the next section, we start with some applications. The first application is kind of these story problems. For those of you in physics, this should kind of sound a little bit familiar because this looks and has the feel very much of a physics problem. The one thing that we have to be careful about on these story problems involving navigation is when we talk about like courses and bearings, this is a different way of measuring an angle. So when we talk about a bearing or a course, the angle starts at north and rotates clockwise. So the first thing we're going to need to be able to do is to convert these bearings and course measurements into standard angle measure. That is where we start at the positive x-axis and rotate counterclockwise. So this is an important piece. If you don't do this, you're never going to get any of the right answers. And don't ask me why that navigators have decided to measure angles in this fashion. I don't know why they've decided to do this, but it's an important conversion that we have to kind of start each one of these kinds of problems by doing. Okay? So I'm going to just kind of read. I'm going to scroll down to where you won't be able to see the problem anymore. But I'm going to read it aloud and kind of make some notes about it as we go, okay? So we're going to start answering the story problem now. So it says a boat leaves a port and averages 20 knots, traveling for 2 hours on a course of 215 degrees. So when we say knots, this is a measurement of speed. Yes. Can I what? So a knot is a nautical mile per hour. I don't know what the difference between a nautical mile and a regular mile is. I have a feeling it has to do with like curvature or something. I don't know. What? I mean, obviously it's on water, sure. But I don't know if like the length is different or something. I don't know. It's really immaterial to the problem. It might have, because you're going like up and down on, I don't know. Yeah.
This is critical. I'm not going to.
Sure. We need to look this up. That's fine. Fine. There you go. Yeah. So that's a lot more than a mile. So it's equal to 1.15 statute miles, which I think is the land mile.
It was defined as 1 minute of latitude and longitude.
There you go. So when it says minutes like that, it doesn't mean minute in time, but like the. Yeah, that makes sense. So when they say minutes, they don't mean like time, but the in between two like lines of latitude or longitude, between the single degree, they count the decimals there as minutes. And then the second decimal point is like seconds. So it's it's like a very bizarre like set of units of measurement, but that's just how they do that. Okay. Anyways, so we have that the boat leaves the port and averages 40 knots, traveling for 2 hours on a course of 215 degrees. So if I do 40 knots for 2 hours, how many nautical miles have I gone then? And I'm just going to call those NMs for nautical miles. I think actually they do this. I think is the abbreviation. Everybody's okay with that. And it says the bearing is 215 degrees. Actually, let's draw that in black. So we start at the north line. So if I think about the XY axis like a compass rose, so we're starting at north and we're going 215 degrees clockwise. So here's like 90 degrees. There's 180 degrees. And then like, what is it? 35 more. Everybody, oops. Okay with how I got to 35 there. But I don't want my angle measured this way. I want my angle measured this way. Okay, so it would be 90, 90 more, and then what does this spot gotta be? 90 minus 35, which is 55. So 90 plus 90 plus 55 is 235 degrees standard form angle. So for us to use sine, cosine, tangent, etc., we need to have a standard form angle. Okay with that? Okay. So what I'm going to do now for this first leg of our trip, I'm going to convert this into a component form vector. And I'm going to call this vector v, say. The problem then says the boat turns to a bearing of 162 degrees and travels 55 knots for 3 hours. So 55 knots for 3 hours gives us how many nautical miles? 165. And it says our bearing is 162 degrees. So again, we're starting from the north. So I go 90 and then 72 more. Will give me 162. But I don't want a bearing, I want my standard form angle. So 90, 90, 90, and this missing spot must be 90 minus 72, so 18. So that's going to be 288 standard form angle. Everybody okay with how I did that? Then I'll call this vector W, will represent the second leg of our trip. So converting that into component form. I can do that. Is everybody okay with what we've done so far? So we had 2 parts of our trip. We do something, then we turn and go somewhere else. So I took the first leg of our trip and converted that into a component vector, or component form vector. And I took the second leg of our trip and converted that into a component form vector. So to get it then says, what is the distance and bearing of the boat relative to its starting position at port? So it wants to know the resultant. So we're looking for a vector r, which is going to be v plus w. So when I type this into my calculator, 80 cosine 235 plus 165 cosine of 288 gives me about 5.10. And then when I do 80 sine 235 plus 165 sine 288, I get negative 222.46. So that's the component form vector of this resultant, what I'm looking for. What I'm going to do now is I'm going to take this component form vector for the resultant and convert it back into a magnitude and direction vector, just like we did at those last 3 problems on the previous worksheet, or the worksheet we just did. So to calculate the magnitude for vector r, the square root of 510 squared plus negative 222.46 squared, which comes out to be about 222.51 nautical miles. So there's the distance we are from the port. Now to find the direction, just like we did before, we're going to draw our picture. So if I go 5 over and, negative 200 down, it's going to look something like that. So if I draw my picture, I have 510 on this side and 222.46 on this side. So to find this angle, which I'm going to call alpha, I'm going to do tan inverse of opposite over adjacent, bless you. I type this into my calculator, I get 88.69 degrees. And if I want the bearing then, that's again starting at north, going that direction, so it's 90 and then alpha. So that's going to be 178.69 degrees. I'm sorry, you asked some kind of a question, but it sounded like mostly mumbles.
So you did not post that?
Right, because it asked for a bearing, not the standard position angle. So I started at north and rotated clockwise to find that. So it's gonna, the addition is a little bit different, right? If I were to do the standard position, I think that would be like 360 minus 88.69. Give you like 271.12 or something. Well, I just called it a bearing. So you could call it theta if you want. Alpha is the symbol I use inside of the reference triangle. The big angle that I'm looking for then is theta. So again, because this asked for a bearing, the way I found that final angle theta was a little bit different than I would if I just wanted the standard position, the direction, as we've been calling it previously. For these navigation problems, they like to use bearings, so we have to be a little bit careful there. I'm stopping here. So you should try to finish the worksheet if you haven't done that yet. And then for homework, let's see.